When you see a self-driving car navigate a really chaotic intersection, or a drone just perfectly inspecting a massive wind turbine, do you ever just stop and wonder, how in the world does it do that? I mean, it seems smart, right? But what's actually going on inside that machine's brain? How does it get from seeing the world to actually doing something? Well, let's pull back the curtain and break it down.
Because that's the real question, isn't it? We see the end result. The car hits the brakes, the drone avoids an obstacle, but the thought process behind it? That's the mystery. So in this explainer, we're going to literally map out the mind of an AI agent, piece by piece.
So here's the game plan. We're going to start with the hardware, the actual physical body of the AI. Then we'll dive right into its mind to see the four-step process every single decision goes through. From there, we'll check out the different ways AIs can think, how they hunt for their goals, and finally, the really cool part, how they figure out the absolute best path to get there.
Okay, first things first, the physical body. It's so easy to imagine AI as just, lines of code floating around in the cloud. But here's the thing. Every single thought, every calculation has to happen on a physical piece of hardware. This is the foundation for everything else. And it all boils down to this really simple but super important equation. In the world of AI, an agent is the whole package. It's the physical architecture, that's the body, plus the program, which is its mind. You absolutely cannot have one without the other.
So this architecture, this body, it's really made of three main parts. First, you've got the sensors. Think of them as the eyes and ears, things like cameras and microphones that let it take in the world. Then you've got the actuators. These are the hands and wheels, the motors and propellers that let it actually act on the world. And right in the middle, connecting everything, is the computing platform. That's the central nervous system, where the program, the mind, actually lives and runs.
And what's wild is how much this hardware dictates the agent's potential intelligence. I mean, think about it. A tiny low-power microcontroller inside a thermostat, it's got just enough brain power for some really basic if this, then that rules. But if you're a Mars rover and you need to analyze complex terrain using deep learning, well, you're going to need the horsepower of a massive server. The body puts a hard limit on what the mind can do.
All right, so we've covered the hardware. Let's make the jump to the software. If the architecture is the body, then the agent program is the mind. And that mind, it turns out, follows a very clear four-step pipeline for every decision it makes. Yep, every single decision flows through these four stages. It all starts with the percept handler. This thing takes in all the raw data from the sensors, like a flood of pixels from a camera, and translates it into something meaningful. Next up is the internal state, which is basically the AI's memory. It keeps track of what's happened and even tries to predict what might happen next. Then comes the star of the show, the logic engine. This is the core decision maker. And finally, the action generator takes that decision and turns it into an actual command for the body. Let's make this real with a traffic light. Okay, so the percept handler sees millions of pixels and translates that chaos into a simple concept, red light. The internal state then goes, okay, I'm at an intersection and the light is red. The logic engine checks its rulebook and decides, brake. And finally, the action generator sends that physical command to the wheels to stop the car. See, translate, remember, decide, and act. It's that same flow every time. Now, that logic engine we just talked about, it's not a one-size-fits-all kind of deal. There's a whole spectrum of AI minds, ranging from something as incredibly simple as a thermostat to things that are way, way more sophisticated. And this table lays it out perfectly. On the simplest end, you've got a simple reflex agent. That's your thermostat. It just follows basic if-then rules. Remember that little microcontroller we mentioned? That's its home. A step up is a model-based agent, like a self-driving car. It uses memory, an internal model of the world, to keep track of things it can't see right now. Then you've got goal-based agents, like your GPS, which actively search for a path to get to a specific destination. And at the very top, you have utility-based agents. Think of an investment bot. It doesn't just find a goal. It tries to find the outcome with the highest utility, or what you might call a happiness score, like maximizing profit. So let's zoom in on those goal-based agents for a second. How does something like a GPS or a game AI actually figure out the route? It's not just magic. It's a really methodical process of searching through all the possibilities. The way the agent does this is by building something called a search tree in its mind. You can think of it like a map of every possible future. The root of the tree is right where you are now. Every branch that splits off represents a possible action, like turning left or turning right, and each new point or node is the outcome of that action. and there are two fundamental ways an AI can explore this mental map. The first is breadth first search, or BFS. This one is wide and shallow. It checks every single option at its current level before moving any deeper. This is great because it guarantees you'll find the path with the fewest steps. On the other hand, you have depth first search, or DFS. This one is deep and narrow. It picks one path and just dives all the way down until it hits a dead end, then it backtracks. It can be way faster at finding a solution, but there's absolutely no guarantee it's the best one. So, finding any path to the goal is one thing. But what actually makes a path the best one? Because let's be real, it's not always just about the fewest number of turns. We need to bring in a new idea: cost.
Exactly. Think about it. A route with 3 turns might only be 5 miles long, but a different route with just 2 turns could be 50 miles. Or maybe a delivery drone taking a direct path over a mountain uses up way more battery than just going around it. The number of steps just doesn't tell the whole story. So to solve this, we need a smarter kind of search, and that's where Uniform Cost Search, or UCS, comes into play. Instead of just counting the steps, it adds up the cost of each step, and that cost can be measured in miles, time, fuel, whatever you want. It's kind of like that breadth first search we talked about, but it always expands the cheapest path first, not just the shortest one.
And this is really the whole point. The second that different actions have different costs, one road has more traffic, one flight path uses more fuel, you need something more powerful than a simple search. Uniform Cost Search is what lets an agent find the truly optimal solution, not just the most obvious one.
So let's put it all together with a final challenge. Imagine you're designing an AI for a firefighting drone. Would a simple reflex agent, one that just dumps water on the first fire it sees, be good enough? Or would you need a sophisticated utility-based agent, one that can actually calculate the most critical spot to make a water drop, and then use a uniform cost search to find the most fuel-efficient path to get there, even if it's not the closest one? The kind of mind you design could literally be the difference between saving that forest or watching it all go up in smoke.